Hi everyone, we are from Group C. We'll present about diamond dosimetry.
Introduction. In radiotherapy, the accuracy and precision of dose delivery to the tumor or cancer is associated with better treatment with high tumor control and lower complication after the radiotherapy treatment. It is to achieve the accuracy and precision of dose to delivery to patient. The dosimeter was developed as a device that used for quality assurance and verification of the radiotherapy treatment. Dosimeter known as a device that measures directly or indirectly the exposure of the radiation to the patient. The dose dosimeter has their own function in radiation processing where the absorbed dose and dose rates has been measured with reasonable accuracy. The dosimeter is attached along with the reader that known as a dosimetry system. More than a decade, the dosimetry system has been used over the world to perform the radiation measurements in verification, qualification, or development the new process, especially in new advanced technology. There are many dosimeters with many kinds of their application. The example is ionization chamber, gel dosimetry, TLD, and film dosimetry. This dosimeter has many useful for the treatment where it can increase the accuracy and precision, give small dose and dose rate dependence, and it has high spatial resolution. In this topic, we will focus to diamond dosimeter. Diamond dosimetry is one of the type of dosimetry that usually used for the radiotherapy treatment. As we know, the natural diamond has a carbon atom that arranged at the center of the cubic crystal structure that are called diamond lattice. Diamond is the one of the most stable carbon where it originates from strong covalent bond atoms. It also nearly tissue equivalent because their atomic number is closely to human tissue effective atomic number. So, the diamond is one of the material that very suitable material that can be developed as a radiation dosimeter. The diamond dosimeter is known as a solid state and their sensitive volume has developed from natural diamond. This detector is suitable for the measurement of dosimetric parameter because this dosimeter is small size, high dose response, and directional independence. There are two types of diamond dosimeter. Diamond dosimeter consists of natural and polycrystalline chemical vapor deposition or known as CVD type diamond detectors. For the natural diamond dosimeter or detector, it is a good quality. However, it is very expensive because it is difficult to find a suitable specimen with right properties. For the CVD type diamond detector, it is known as a cheaper detector, small size, and has high sensitivity of intensity modulated radiotherapy or known as IMRT beam dosimeter.
Diamond dosimeter is the one of solid-state dosimetry. This figure shows the example of the band principle in a solid-state dosimetry where the periodic lattice of a crystal allows energy band for electrons to exist. The valence band is the energy level of the atomous electrons. Above the valence band, there is a conduction band separated by the band gap, which for the diamond is 5.5 electron volts. In the conduction bands, the electrons can freely move around. Energy level in between the valence and conduction bands are forbidden unless the lattice has been distorted either by impurities or dislocations. These sites can act as traps for electrons or holes because they are immobilized here for a relatively long period of time. At shallow traps, electrons or holes may jump easily from the trap sites to the conduction or valence band by excitation or de-excitation of the particle. Next, the principle of the diamond dosimetry. The diamond detector is in principle a solid-state ionization chamber. When ionizing radiation is incident upon it, then the ion pairs are created. The electrons can move around in the conduction band of the lattice, and applied bias voltage from the 10 to 500 volt secures the collection of the charge by attracting them to the electrodes, and the resulting charge are proportional to the radiation dose rate. Furthermore, the electrons at the traps create space charges which give rise to an electric field opposite to the applied bias. This concept, called polarization, which decreases the collection efficiency, rendering once again a nonlinearity of the detector. The increased number of space charges as the diamond is irradiated causes a decreased bias and thus a decreased charge collection efficiency, which will give a decreased signal from one measurement to the next. When the traps are filled, all charges go to the electrodes and increase the output signal will accumulate those. The example of the diamond dosimetry in different type of the operations. The diamond dosimeter was used as a colorimetric application by proton interactions, and also was used as spectroscopy application by proton and neutron interactions. Diamond dosimeter also can be used as the beam loss monitors by electron interactions in electron accelerator where the sub-nanosecond time resolution is required. Moreover, it used as a dosimeter in a medical application such as in stereotactic radiotherapy or radiosurgery in a radiotherapy field. Stereotactic radiotherapy. Stereotactic radiotherapy is a treatment used for small tumor like metastasis, and it uses small photon beams. The smaller dimension of the photon beams used in this treatment requires a suitable detector to determine the delivered dose with a high accuracy. The dosimeter used in this treatment has to be as close as possible to tissue equivalence and to exhibit a small detection volume compared to the size of the irradiation field because of the lack of lateral electronic equilibrium in the small beam. The lack of lateral electronic equilibrium in the small photon beams is responsible for the non-accuracy in those measurements performed with active commercially available detectors. Therefore, a single crystal diamond has almost tissue equivalence material, which the atomic number of the diamond is 6, that close to that of tissue, which is 7.4. Therefore, the high density of diamond properties make it an ideal dosimeter to fulfill most of the small beam dosimetry requirements and to avoid the perturbations of lateral electronic disequilibrium.
Next, we move to the dosimetric properties of the diamond dosimetry. Firstly is the fractional dose curve, followed by linearity, and then long-term or time stability, and lastly energy dependence. The first dosimetric properties is fractional depth dose curve. The central axis fractional depth dose curve measured by synthetic single crystal diamond detector (SCDD) and reference ionization chambers is shown in the figure. The curves are normalized at 10 mm depth in water in the plateau region. In some cases, a best fit in the entrance region by an exponential growth function was used to extrapolate depth dose values. No corrections were applied for dose rate effects or for water to detector material stopping power ratios. This figure also shows fractional depth dose curve from biosynthetic single crystal diamond detector and Marcus parallel plate ionization chamber in 155 and 250 mega electron volt proton beams with 14 cm square QA aperture. A detailed analysis of depth dose curve was performed by using parameters recommended by ICRU report number 787, which are depth of penetration and distal dose fall off (DDF). Depth of the penetration is known as the depth in water on the central beam axis in which distal 90% of maximum dose is obtained, and the distal dose fall off (DDF) is defined as the distance on the central beam axis between points representing distal 80% and distal 20% of maximum dose in the decreasing part of the bright peak. The next one is linearity. According to Talamonte et al. 2014, synthetic diamonds shows a very good response linearity versus absorbed dose in the range that is appropriate for the use of the dosimeter in conventional radiotherapy, which is 1 to 10 gray. The linearity of the charge versus absorbed dose at lower doses is also of a concern when the suitability of a chemical vapor deposition (CVD) diamond detector for IMRT application has to be assessed. In the paper by De Angelis et al. 2007 about a polycrystalline CVD detector, the 0.1 to 1 gray range was investigated. The residual analysis shows that for low doses less than 0.3 gray, the deviations from linearity are quite large and they reach almost 20% close to 0.1 gray. This was attributed to the non-optimal dynamic response of the device, which takes a few seconds to reach the steady state, which is equilibrium current. For single crystal devices, this problem does not exist in the range of 0.04 to 50 gray. Almaviva et al. 2008 reported that a deviation from linearity of less than 0.5%, with the exception of few very low doses data affected by scattering due to noise and or accelerated instabilities. So the next dosimetric properties is long-term or time stability. According to Marsola et al. 2020, the long-term stability was studied by irradiating the synthetic single crystal diamond detector in a cobalt-60 beam. The diamond detector was polarized at 50 volt with a Keithley 6517A electrometer, and the signal was measured during a succession of long-time irradiation, which is 3 hours and 30 minutes. After a pre-irradiation of about 5 gray, the stability of the current over the whole irradiation was analyzed according to the LNHB requirements. So, this figure shows the maximum current variation of the SCDD with respect to the first current value after a pre-irradiation of 5 gray over about 17 hours of measurements. The maximum current variation of the SCDD is lower than plus minus 0.1% and respects their criteria. Lastly is energy dependence. Even though diamond is a near water equivalent material, the energy dependence property is related to the entire device, while context and encapsulation may introduce some effects. In the literature, a few papers are found where a specific analysis on the response dependence of the detector on the radiation energy is reported. According to Fowler's theory, the response of natural diamond is expected to be dose rate dependent. Many studies in the literature were devoted to investigating the performance of diamond versus dose rate. The dose rate dependence of diamond was studied in photon, electron, and proton beams. In particular, different values ranging from 0.90 to 1 were reported in a wide dose rate range obtained by varying both the dose rate and pulse repetition frequency or PRF of the accelerator.
Let's get into the practical consideration using diamond dosimetry and its reliability to the radiotherapy field. First, we have to consider the positive dosimetry properties of diamond and whether diamond is a reliable material to be used in radiation detector. On the top, we see diamond have near tissue equivalent, where carbon in diamond has atomic number of 6, which is rather close to tissue's atomic number, which is at 7.4. On the left, diamond has high band gap energy, which leads to lower leakage current when compared to semiconductor, causing diamond to have less an acceptable signal-to-noise ratio. On the left bottom, we see that diamond has quite high radiation hardness, and this radiation hardness arises from diamond's low atomic number and high atomic displacement energy of 42 electron volt per atom, meaning that the covalent bonds across the diamond lattice structure are very strong, and diamond's radiation hardness is higher than silicon. On the right bottom, you see that diamond has high radiation sensitivity, which arises from its high W value. Although charge pair production of diamond is lower in comparison to silicon, but is higher than gas detector. Lastly, diamond has a fast detector response, which is due to high mobility of free charges in the diamond, which implies fast charge collection and overall response of a diamond detector. This table shows the comparison properties of diamond and silicon. From this table, we can see that diamond has a high displacement energy, W value, band gap energy, and electron mobility. Diamond also has a lower dielectric constant, which leads to lower capacitance in comparison to silicon, which have similar dimensions. Besides these properties, diamond also has high resistivity. This is due to diamond's strong covalent bond, making diamond being able to withstand high temperature and be temperature independent. This results in diamond detector being able to be used in higher temperature in accuracy in compared to other detector, because this is not seen in all detectors. From this graph, we can see that polycrystalline diamond detector has a lower resistivity than a single crystal CVD diamond, which means that single crystal CVD diamond can withstand higher temperature and be used in higher temperature compared to a polycrystalline CVD diamond. The two types of diamond source, the natural and the synthetic or CVD diamond. The natural diamond is not used widely because of its poor availability and high cost. This is because finding natural diamond that is suitable and high in quality for radiation detector is rather hard. On the other hand, chemical vapor deposition diamond, CVD diamond detector is cheaper to fabricate. The cheaper fabrication making it not scarce, and it makes it to have less cost. Other than that, CVD diamond also has reproducible characteristics. This is done by fixing the high temperature and pressure value, plus maintaining the fixed carbon source. Through these measures, the wanted CVD diamond characteristic can be produced The early type of CVD diamond detector composed of polycrystalline CVD diamond detector. The polycrystalline diamond detector has its crystals in different size and orientation, and this causes polycrystalline CVD diamond detector to have some unfavorable characteristic. It has a problem of leakage current, high priming doses, small photocurrents which leads to low sensitivity, non-linear relationship between photocurrent and dose rates, making it less accurate, and non-uniform collection boundary, and it has a crystal ingrain effect. The priming dose is needed for a crystal diamond detector to saturate the amount of space charges via irradiation to stabilize output signal of a detector. Single crystal diamond detector has its diamond crystal in the same size and orientation. And this single crystal diamond detector is that compared to polycrystalline has extremely low to zero dark current of less than 1.25 picoampere. It also has a lower priming dose, which means that lower irradiation is needed to prime the crystal. It has higher sensitivity than polycrystalline diamond detector, and it also has a linear relationship between photocurrent and dose, which makes the reading more accurate. However, there's one problem. The pre-irradiation procedure of a single crystal diamond detector is rather unstable now. So more examinations, more experiments are needed to fix the quality, the characteristic of a single crystal diamond detector, which is optimal, and also standardize the prime dose procedure. And this pre-irradiation procedure is actually related to the prime dose needed and its resting time. This concluded that a diamond is highly reliable as a radiation detector for radiotherapy due to its high accuracy and precision because of its rather high charge pair production speed compared to gas detector. It has a linear dose response to photocurrent, high spatial resolution, and being temperature independent. This temperature independent is a very good factor for it to be used in radiotherapy field. The graph on the right shows the linear relationship of photocurrent to dose rate of a type of diamond material used in diamond detector experiment. Among the diamond source, single crystal CVD diamond is the most suitable diamond material for radiation detector. This is because it is cheap and easy to fabricate. This is an important factor to have a fixed standard diamond detector. However, in use of single crystal CVD diamond, formulation of a standard best suited CVD diamond for fabrication need to be experimented, and the development of its prime dose protocol is also important when it comes to a diamond.
As we know, the diamond dosimetry is one of the devices that can detect many types of radiation. This advanced technology has been used widely and had improved their device until now. Every type of dosimeter has their own advantage and disadvantage in order to complete the system. There are few advantage and disadvantage that can be focused in diamond dosimeter. Firstly, the advantage of diamond dosimeter is nearly tissue equivalence. As we know, the diamond is one of the most stable carbon. When it compared the atomic number of diamond with the human tissue, it shows that the atomic number of diamond is closely the human tissue effective atomic number, as the atomic number of diamond is 6 while human tissue is 7.5. So, the diamond dosimeter is more effective in detect the radiation to human body. Besides, the diamond dosimeter also require nearly no energy correction. It is due to the energy that absorbed by diamond is similar with the energy that absorbed by human tissue. So, this advantage will reduce the needed for energy correction mechanism with the other semiconductor materials. Thing, the diamond dosimeter is waterproof device where this kind of dosimeter can be used for measurement, especially in water phantom. The dosimeter also is very low leakage current and provide high signal to noise ratio when the detector has exposed to ionizing radiation. Other advantage in diamond dosimeter is high sensitivity, general stability of detector response, and also good time resolution. Don't forget, they are suitable for usage in high dose gradient region, especially in stereotactic radiosurgery. Even though the diamond dosimeter has a lot of advantage, the dosimeter still has some disadvantage of weakness in their tools or device. For this diamond dosimeter, there are a few disadvantages that can be focused. First, the research has been shown that the diamond dosimeter has energy dependent. This energy dependent will be effect on the contact material and also the construction of the detector. Besides, the CVD diamond detector has low dynamic response. Due to this weakness, the diamond is not suitable for the IMRT application because this detector is impossible to sharp the transition of IMRT fields. In order to stabilize the dose response and reduce the polarization effect, this dosimeter must be irradiated when it used. The disadvantage of this dosimeter is they had specific voltage. If the voltage has applied higher than the specific one, it can immediately destroy the diamond dosimeter. Lastly, the diamond dosimeter has developed small dependence on dose rate. So, when the diamond dosimeter has measured the depth dose or absolute dose, the correction factor must be done to correct this problem.